Assalamu alaikum. My name is Zohaib and today I'll be presenting on computational linear algebra with Matlab. Linear algebra is foundational in many fields. In this presentation, we'll explore how Matlab helps us solve linear algebra problems, such as solving systems of equations, calculating eigenvalues, and performing matrix decompositions. By the end of this presentation, you will understand how computational linear algebra drives real-world applications. Introduction to computational linear algebra. What is computational linear algebra? Computational linear algebra involves using algorithms to solve problems related to matrices and mainly vectors. This also includes operations like solving systems of equations, finding eigenvalues, matrix factorizations, and more. It allows us to handle large-scale problems that can't easily be solved by hand. For example, large systems of linear equations are common in fields like machine learning, computer graphics, and engineering. Linear algebra is essential in many fields, data science, for example, in analyzing and uh, reducing the dimensionality of large dataset using techniques like PCA. Then in machine learning, for algorithms often require matrix operations for tasks like optimization and regression. Physics and engineering used in simulations, modeling, and problem solving. Computer graphics used to manipulate images and perform geometric transformations. Without computational linear algebra, solving these problems would be incredibly slow and inefficient. Why Matlab for linear algebra? Matlab is a high-level programming language basically designed for numerical computations. Its core strength lies in handling metrics and different vector operations efficiently. This also makes it the ideal environment for solving linear algebra problems. Matlab simplifies many complex tasks. Unlike other languages, Matlab has many built-in functions for matrix manipulation, eigenvalue calculations, matrix inversion, and more. The backslash operator, for instance, is optimized for solving systems of linear equations and is much faster than manually applying algorithms like Gaussian elimination. Matlab offers matrix centric. The matrix is the primary data structure in Matlab, making it very intuitive for linear algebra. Optimized algorithms. Matlab uses highly optimized routines for common linear algebra tasks. Then comes visualization. Matlab includes powerful plotting functions to visualize matrices and transformation. Now we have many basic matrix operations that we can use in MATLAB. For example, one of them is matrix creation. Creating matrices in MATLAB is very straightforward. You can pretty much initialize matrices filled with zeros, ones, or random numbers. To create a 3 by 3 matrix of 0, we simply use b is equal to zeros bracket 3 comma 3 bracket close function. Then there is a function to create a 2 by 2 matrix of ones, which is c is equal to ones bracket 2 comma 2 bracket close. Then there is another function that creates a 3 by 2 matrix with random numbers, which is d is equal to r a n d bracket 3 comma 2 bracket close. Then there are basic operations. Once you have matrices, you can easily perform operations. Addition, C is equal to A plus B adds two matrices element wise. Multiplication, C is equal to A multiplied by B. It basically multiplies two matrices following standard matrix multiplication rule. Then furthermore, we have the precision of transpose, in which we use C is equal to A naught. This transposes the matrix by swapping rows and columns. Then we can also calculate the inverse with the inverse function, which is inv, and in the bracket we have the desired matrix. This computes the inverse of a matrix if it exists. Then there is another important operation that we apply on matrix in Matlab, that is calculating the determinant, which is det bracket a and this returns the determinant of the matrix, which can indicate whether a matrix is invertible or not. Then solving system. Now we'll talk about solving systems of equations. A system like ax is equal to b can be solved for x, where a is a matrix and b is a vector. Matlab provides a simple and efficient way to solve these systems using the backslash operator. For example, if we have to solve two matrices A and B, you simply type x is equal to A slash B. This quickly computes the solution x. The backslash operator is efficient because it automatically selects the best method for solving the system, like LU decomposition, without needing the user to specify it in simple words. Eigenvalues and eigenvectors. These can be calculated very easily using the algorithm of Matlab. Basically, what are eigenvalues and eigenvectors? Let's now look at both of these things, which are key in many linear algebra applications. For a matrix A, an eigenvector V and eigenvalue V satisfies A multiplied by B is equal to lambda multiplied by B. Eigenvectors represent directions that are stretched or compressed by a matrix, and the corresponding eigenvalues tells you how much stretching or shrinking happens along that direction. To compute eigenvalues and eigenvectors in Matlab, we use the EIG function. To find the eigenvalues and eigenvectors in Matlab, we type bracket v comma d bracket close equal to the eigen function, and in the eigen function bracket we place our desired matrix. Here v contains the eigenvectors and d is a diagonal matrix with the eigenvalues. Now there are some applications of this eigenvalues. Eigenvalues and eigenvectors have many applications, such as principal component analysis in data science, helps reduce the dimensionality of datasets. In quantum mechanics, eigenvalues help describe systems at the atomic level. Vibration analysis in engineering uses eigenvalues to model the frequency of oscillation. SVD, also known as singular value decomposition. What is SVD? Now let's discuss it. SVD is a factorization method that decomposes a matrix A into further three matrices. For example, we can decompose A is equal to U into V into X. Here U and V are orthogonal matrices containing eigenvectors, and X is a diagonal matrix of singular values. These singular values tell us how much of the data is important or significant. Matlab function. In Matlab, you can compute the SVD of a matrix using the SVD function, which is typing SVD bracket and bracket close. An application of these SVD, which is widely used in data compression. By keeping only the largest singular values, we can compress data very efficiently. Then it is applied in image compression. SVD helps compress images while preserving essential information. Further on, recommender system SVD is used in algorithms that also suggest products or movies based on user preferences. For example, we have the example of Netflix or Amazon for this. Now we have some key applications of computational linear algebra in the real world. Computational linear algebra is crucial in many fields. CLA contributes to 85% usage across industry in data science, which is a pretty big portion to be considered. Machine learning contributes 92%. Linear algebra underpins much of machine learning from optimization to dimensionality reduction. Moving on to physics and engineering, which covers 78%. Physics and engineering is used in simulations, modeling, and analysis of physical systems. Next, we have computer graphics, which refers to 65% in usage across industries. It is essential for transformation, rotations, and 3D rendering of images. Matlab not only simplifies these operations but also provides the speed and efficiency needed to tackle large real-world problems. To summarize, Matlab provides powerful tools for solving linear algebra problems, whether it is performing basic matrix operation, solving systems of equations, or using advanced techniques like eigenvalue decomposition and SVD, which we talked about earlier. Matlab makes it simple to work with matrices efficiently. I highly encourage to explore Matlab's advanced features such as sparse matrices, parallel computing, and optimization techniques. That is all for Matlab from my side. Thank you for your time.